So now we are ready for adding the convolution layer. And in the slides, in the convolution layer, I add the kernel library. And the idea behind that is if you want to start with adding your convolution layer, then if you want to test your code, you can use the kernel from the library because you know already what the convolved images are supposed to look like. In practice, however, you do not start with actual kernels because the values in the kernel, so the weights, they will be learned during the training process. And that's what I want to do here as well. So we want to add our convolution layer, and we will copy and paste lots of stuff that we had already in our self-made convolution function here, especially those nested loops here. So I want to start with an init, where we give the kernel shape an x direction, let's say it's 3, and the kernel shape in y direction. Let's say the default is also 3. And we also want to add the number of kernels we want to have. So the kernel number, let's say 10 or something as a default setting. Okay. So now we want to also remember those values and use self. So we want to remember the kernel shape in both directions, and they will be normally the same number. And we also want to remember the kernel number. So the number of kernels, how many kernels do we have? All right. So now, as in the slides, we would now add this kernel library and call this kernel library. But as I said, these values are learned during the training process. And since those values are learnables, we want to use our optimizer for that. We want to call them weights. Remember, the optimizer looks for the attribute weights in the layer and then applies the gradient descent and also with momentum, so the entire optimization to our layer. And it does it for the weights and the biases. So it looks for this particular attribute. And therefore, if we just call them weights and they have the same meaning as weights, it will update them accordingly, and we can use the same optimizer in the same way. So the kernel now are called weights. So the content of those kernels, so those values here that you see here, they are now called weights, and we want to initialize them randomly. So we use random and random, normally distributed random numbers. Let's say you multiply them with 10 or something, and then the size is the shape of the kernels, x and y. And of course, the number of kernels. And we also want to save the biases. And that's new now, because we also want to add the bias part. How many biases do we have? So the idea is that every kernel is like a neuron. And you can actually see that here. So here we would have just 9 inputs. And all those inputs have different weights. In this case, just this one weight, just this one input has one weight, which is not 0. So we would just sum up all those values because that's what convolution does, right? We multiply those pixel values with the corresponding pixel value in the image. We do the same with all the other pixel values and sum them up. And if we add a bias, then mathematically, it's the exact same structure that we have in an ordinary neuron. And that's the whole idea. So these convolution kernels are actually neurons. And we want to learn these weights here. Same here, right? Then we have different weights, -4, +1, but they might not be the correct weights or the optimal weights. So we want to train those weights, or the network that learns those weights. And we always add a bias. So we just add a bias. And how many biases do we have? Well, if one kernel, convolution kernel, acts as a neuron, then we have as many biases as kernel. So we have a vector which is just has the size 1 times kernel number. So you see the whole thing becomes more serious now. So we initialize these kernels now. And we also want to add a forward method already. And in the forward method, we essentially want to do what we did here in convolution self-made. So we pass on an image, and we get this image in the first step, so in the first convolution layer from here. And let's call this image just M. Then we want to add padding and stride, so we can just copy and paste what we had here. And then we essentially just perform the convolution. So what do we have to do? So we go to our forward part. And first of all, we determine the shape of our image M, or our matrix M. And what do we get there? So first we get the shape of the image. And remember, when we have our matrix M, let me just remove that here. We have the images scaled. So that's the X shape of the image. And then we have the image Y shape. And then we have the number of channels. And let's call it number of channels. And then we have the number of images. So we have the number of, so the shape in X, in the Y direction, the number of channels, and the number of images. So then we also want to just copy and paste our code here. So we have to remember what YK and XK is. So what is YK and XK? Well, we have to save it as self kernel shape. So this is our XK. And this is our YK. There's one additional variable. That's the number of kernel. So let's call it NK, number of kernels, and that's what we have here, self-kernel number. That's what we get from the init. I also want to call the biases. And we want to already think about the backpropagation, which we will do later, of course. but there are a few things we need to store for the backpropagation. We can do that already now. Therefore, let's write something like this. We are going to need for backpropagation, and we need the padding. Just imagine you want to do the backpropagation, you have to do kind of the same stuff backwards, so that's why we need the padding. And we also need this stride length. Okay, so now we can actually start already with our copy and pasting, so to say. So we have the shape of the image, we have padding and stride, so we can create so we know what X and Y output will be. And we can also copy and paste output already. Number of channels, but now also we have number of kernels. And we also want to, so after we call the biases, we of course also want to call the weights. And let's call that just W. So these are just the cell weights. During the training, it might be that we sometimes get NaN because it goes off, because we can have underflow or an overflow, and we wanna somehow, so we wanna avoid that when we get an NaN, that it kind of screws up the entire training process. And there's a trick in Python. You can just say np NaN to num, which just saves the largest possible number that actually makes still sense. Because we know it's a very large number or it's a very small number. In order to prevent this NaN stuff, we can actually apply this NaN to num. So just something like a checkpoint that we still can go on with our training process, even though we might have a few values that freak out, but maybe we still have a good result. And that's the reason why we do that. Okay, so we have now the output. We have the coordinates and we have the output that we want to have. What else do we need? So how would it continue now? Well, we want to create a padded image. So we can just copy and paste this part. It's the same idea. Now we have the padding, we have the number of channels, plus we have the number of kernels. And we also have the number of images. So we also have to add the number of images for the output. And because we want to have padded images, here we add the padding as before. We want to do this for all colors, for all kernels, and for all images. And we have to do the same thing here as well. So it becomes a bit more complicated now. But I hope you see it's still the same idea. Okay, so our matrix M has the size or the shape X, Y, number of kernel, number of images. So what we would do now in the next step is putting our image into our padded image. So our image now is called M. And we want to do this for X and Y. That's the same as before. But then we have the number of channels. And we want to do this for all the images because M contains these images already. But we want to run this image through all the different kernels. And the number of kernels is the second last dimension. And we want to do the following now. So we have our image, X and Y. Then we have all the colors. And we have all the images. That's what we have in M already here. But we want to run a loop now where we want to perform the convolution for all images, for all colors, but with all kernels. So therefore we prepare this matrix image padded with number of channels, number of kernel, and number of images. And we have to put this image then into the center. We do this with all color channels, but we have to do this for all kernels. And if we have this part here, we do this for all images at the same time. So we want to write a loop where we just say for k in range number kernel, we just put this image M in this matrix for every kernel. So think about it. If it's not initially clear to you, let me just get some space here. That we just feed in the image or the matrix with all the images here in our image padded, because then we have all those images for all colors and for all kernels padded in the same way. So let's go back to our convolution self-made. What would have been the next step? So the next step actually is running the nested loop. So let's copy and paste that. Let's see whether we can run this loop in the same way. So we have the number of channels, we have the number of, we have the coordinates y in x. What else do we need now? So we also have to do this for all kernels and for all images. So we actually have to add one more loop. So add two more loops actually. So first of all, we have to go for I in range number of images. So we have the number of images. Okay. And then let's do the following, that we don't lose track and get too confused. So let's extract the current image, the current padded image. So how do we do that? So we take all rows, all columns, all colors, all kernels, and the particular image. And that's our current images, current image pad. So now we have selected one particular image. But we want to perform the convolution for all the different kernels, for all different channels. So let's say our next step is performing convolution for all the different channels. And then we want to do this for all the different kernels. And still we have to do this for all the coordinates. And now I guess you see why using lots of nested loops will make the code actually slow. So we have 1, 2, 3, 4, 5 nested loops. But still I want to do it this way that you really see what's going on, right? So we extract the current image, then we go over the color channels, and we go over the different kernels, and then we go over the different coordinates. So that is kind of straightforward here. So we just have to make sure that we shift it a bit more to the right. So then we have the stride, and then we have our current slice. So let me just move this here first. So we get our current slice. But this time it's for the current headed image. It's for the particular channel, that's still true. So let me just add the line break here. That's for the particular channel, but now also for the particular kernel. Remember, the order was channel, kernel, image. We selected already particular image. Now it goes over the particular kernel. So now we perform this multiplication here with our particular kernel. So we take the current slice and we multiply this with our particular kernel. What is our kernel now? Remember, we put the weights into our matrix that's called W. So we go to W. And what was the shape of W? So that's the shape of weights. And what is the shape of weights? It is the kernel shape in X and Y times the kernel number. So if you go to W, we have to extract all rows and all columns because that's our kernel shape for this particular kernel. Because K runs over the different kernel. And now we have to put this into our output. What is our output now? So our output goes over C. So X, Y, the color channel C, but then the corresponding kernel K and the corresponding image I. And leave some spaces that it's not getting too crowded. So that would be the normal convolution part. But then we said our convolution kernel have the same structure or should have the same structure as a neuron. This part is the weighted sum of all those inputs because here are our weights. So what is missing is the biases. So let's go to our bias. What is our bias? So our bias is this here. So we get our bias B, and therefore we have to add the bias from the corresponding kernel. So just to make sure that we really have what we need. So it's bias 0K. And also let's make sure that we have float. That's lots of work. And I hope you didn't lose track. But exact same idea. The only difference is that we run this loop over the different images and also over the different channels. And of course the different kernels. but essentially it's the same code. All right. So what happens next? So after the loop, so we have to check how far we have to go to the left. So here we are. So after the loop, we have our output. And now we have the convolution over the different color channels. And what is done in the next step is that we sum up the convolution over the different color channels. So we just say output, sum, and over which axis? It's axis number 3, which has the index 2 in Python. So we sum up over all the colors. And that's what I said earlier. If it's a black and white image, we have the same information everywhere. So it doesn't matter. And also we want to save the output. And also here you kind of want to prevent overflow and underflow. So we just use np none to num. Then we want to change save m. And remember in our other codes, we always save this as self inputs. So we saved self output and saved input. And we want to do this in the same way now, because then the code is more compatible. We also want to save the padded image. That's just for checking. Because we did so many things now, we added so much stuff. There's probably somewhere a typo, and we always want to check whether it makes sense what we see. So we just take the image padded. Okay, so that's it. So I compile it, and we have our convolution part here now. Okay, so what should we get actually as an output? So we, first of all, should get an image where the size corresponds to the padding and the stride according to our equation. That's our output image. Then we sum over all colors. So we still should have a 4-dimensional matrix like this, where the number of images is the last entry, but then it should be the number of kernels that we used, which we have as a third entry, because we want to have a convolved image for every filter. So let's see whether we get this kind of result. So let me just import the new ANN again. See, that's not what we want. Okay. And we also want to take a look at the images. So let me just remove those images. And by the way, since we have called those images again, the first image should be a different image now, because we draw them randomly, remember? And it is a different one. So let's also check it's a cat. Yeah, it's a cat. All right. So, and this matrix M contains now all those images with a certain scale. And the scale is 100 times 100. Let's also just check this again. And we have those 50 images. And now we want to set up our convolution filter. So we call our init. Let's call it convolution 1. And we do that with, so we just call it convolution layer. Okay. Let me do that again here in the console. So we have the kernel shape. Let's say we want to have 3 times 3, and we want to have 10 different kernels. Then we have our first convolution layer. We might want to pass the convolved images to the next layer. So let's create a second one. And let's create a convolution layer where we have fewer filters, but maybe we have just larger kernel. So we also have this here. Okay, so now the input is the image with the coordinate, with the padding and the stride. And we want to create an output, which is here. So we just run convolution 1. Okay, so the image is now the matrix. Let's say we have padding. So let me also just do this in the console here, that we have the autocomplete. So we have convolution 1. So we have the image. M. That actually should work. Let me just check. Yeah, of course, it's the forward part, sorry. So that's why I always use the autocomplete. So it's the forward part. And then, of course, we have the image. Then let's actually start with padding 0 and stride 1. So actually default values. So let's do that. And let's cross fingers that we don't get an error message. We get an error message, and let me just quickly fix that. And you see already why it's a typo. So let's fix it. So let's go to the here, and we have weights. All right, self weights, self weights. So we just run this again. And let's see, it's the next typo. So we don't get a typo. We don't get an error for now, and kind of see that it takes some time. But we do this with 50 images. Okay, so convolution it's done. So let's check the output. So the output, what is the shape of the output? So first of all, the shape is the image shape which was 100 minus the size of the kernel, which is 3 in our case, which is 97. There's no padding, stride is 1, so it must be 98. That looks good. We also have 10 kernel, that's 10, and we still have 50 images. So that makes sense. And I also plotted already an image. So let me also just plot the image number 1, for example. And then you have different kernel. So for the different kernel, you would not really see many differences in the images, because remember what we just initialized those kernel. So that seems to work and also makes sense. And if you want to try this with your kernel library instead of the randomly initialized kernel, then you can also convince yourself that they do the right thing. And the idea now is that we have this output, and we feed this output not directly, but in principle, into the next convolution layer, and we just want to check whether that works. So we have the forward part, and the next input image is this then. And let's say we have padding 2, and let's say we have stride 4. Why not? What should we get? So we have a larger filter, so then we should actually get a smaller image, especially when the strides is 4. So we should actually get a smaller image. And let's try to see what we get then. And let's run this part. Since the first part worked, then this part should work as well, because these are just 2 different instances from the same class. And also here, let's run the code and let's see what we get. All right, so code is done. And then let's check the shape. So we have 8 different kernels, so it should be 8. Sorry, convolution 2, of course. Well, we have both now, we can check. It's 8, it's 25. If you do the math, you will see it makes sense. And we also can look at a plot. This is now output 2. And you see the padding at the edge. And you see that it is a lot smaller as well. And it's essentially like blurred. So our convolution layer work, and we can perform now the next step. And before we do that, I just want to go back to our slides and kind of summarize what we did. So let me just go back to the other screen. Okay, so we will typically include many convolution layers. So it will always be like this. We have our image, we pass it into next convolution layer, then this convolution layer will produce another image, and then we want to pass on to the next convolution layer and so on. So that's what we actually did. So, and what you also saw is that the input image has a number of channels, which is the number of colors. Then we convolve it with a certain number of kernels, and the output image has the number of kernels as the number of channels. And this will be the input image for the next one. So in our code, the number of channels always refer to the incoming image, and the number of kernels to their output matrix. Okay, we add this forward part. Just quickly want to go through that, where we have the padding, where we determined the size for the output image. We copied and pasted in principle what we had in our convolution self-made. Then we added those additional parameters, like the number of kernels, the number of images, and then also did this in our loop, so that we have 5 nested loops now. And we also added the bias, and we sum the output over the different color channels. And that's what we always do, and it's what's been done normally as well. Okay, so if you do this with the defined kernels, you will, so first of all, we have now our module here with lots of different classes and methods. And I would really recommend to play a bit with that. So the idea now is that we initialize different convolution layers with the same class, so that we have different instances. And those layers can have different parameters, and that's what I showed earlier. The size of the kernels, the number of the kernels, and then we just run them subsequently. So we feed in the image in the forward part of the first convolution layer that generates an output. We feed in the forward part of next convolution layer, and so on. And if you do this with the fixed kernel values, then you see all these differences. and can play a bit with that. And also when you write the code, make sure that the shape makes sense, and that all those numbers add up. And when you take the defined filters so the standard filters that I showed earlier, then also make sure that the images make sense when you see them. Like in our case, again, we just started with random numbers, and that's what you really do in CNN, because those weights have to be learned. And again, just check those numbers. All right, so then, yeah, and also just check for larger kernel sizes and larger step sizes as well. And then we are done with the convolution part. And now we want to, in the next chapter, we want to talk about a method that's called pooling.